I recently learned that Stanford used to produce its own math contest. If you're familiar with the Stanford Math Tournament, this is a different contest. This was offered from 1946, and they stopped doing it in 1965. It was only for seniors in high school, and the purpose was to attract them to Stanford. It started with just 60 California high schools, and the winner won a one-year scholarship to Stanford. It isn't clear to me if these students also received admission to Stanford or were they already admitted. A few years later, more scholarships were awarded and then some additional cash prizes. Also, more high schools were included on the West Coast. It says the exam was discontinued after 1965 because the math department wanted to devote more resources to graduate teaching. I'm wondering if this also reflects a change in how Stanford handles admissions. Most colleges have an admissions committee that's separate from the faculty departments and receives virtually no input from the faculty. And I'm wondering if that's what the change was in 1965. To learn more about the history, you can get a copy of the Stanford Math Problem Book. It includes a lot more detail about the history of this exam, along with the actual exams, hints, and solutions. I'm going to review the problems from an exam from 1948, but first let's take a look at the rules. We're not allowed to use any notes or textbooks. We have 3 hours to solve these problems. It says good presentation counts. I wonder if this means you'll get partial credit for showing your work. It looks like they're first graded by grad students at Stanford. And it seems like if you're able to solve 1.5 or 2 out of 4 of the problems, then the exams are then read by a faculty member. And then somehow they judge which one is to be the winner and to receive the scholarship. I'm going to solve the problems from the 1948 exam. This exam had 4 questions that I thought were interesting. I'm also going to include the hints because I don't think they were particularly helpful. So let's start with this first problem. Here's the first problem from the 1948 exam. On the left-hand side, it looks like we have these sequences of consecutive integers that are summed, and we should recognize these numbers on the right-hand side as perfect cubes. Well, if we write this as the sum of 2 perfect cubes, just to keep the pattern going, it looks like each of these is equal to the sum of 2 consecutive perfect cubes. So let's generalize. On the right-hand side, we have the sum of 2 consecutive perfect cubes. I'm going to write this as n cubed and n plus 1 cubed. On the left-hand side, each of these sums ends in a perfect square. For example, this last sum ends in 16, which is 4 squared. That corresponds to this 4 cubed over here. This 9 is 3 squared. The 4 is 2 squared. So if this higher perfect cube is n plus 1 cubed, then the largest number in this sum is the square of n plus 1. And we take the sum of all these other numbers, consecutive integers, down to these numbers, starting with 2, 5, and 10. These are all 1 more than the previous perfect square. So 10 is 1 more than 3 squared. So I can write this as n squared plus 1. So we're taking consecutive integers from n squared plus 1 all the way up to n plus 1 squared, and we want to prove that this is equal to the sum of n cubed and n plus 1 cubed. The hint suggests induction, but I feel like we can just expand the right-hand side and come up for an expression that's equivalent to the left-hand side and show that they're equal to each other. Let's start with the left-hand side. We're finding the sum of consecutive integers from n squared plus 1 to n plus 1 squared. I'm going to write this as the sum of consecutive integers from 1 to n plus 1 squared, and I'm going to subtract the sum of the integers from 1 to n squared. So counting 1, 2, 3 all the way up to 16, and then subtracting 1, 2, 3 all the way up to 9 will give us this last line from 10 to 16. We can use our formula for the sum of consecutive integers. If we have n of those, from 1 to n, that's n times n plus 1 over 2. So I'll apply this to our first summation. We're adding the numbers from 1 to n plus 1 squared. So we take n plus 1 squared plus 1 more than that and divide by 2. And then this is the sum of the integers from 1 to n squared. So we'll subtract this. This is n squared times n squared plus 1 over 2. Let's simplify these. First, I'll factor out 1/2 from both of these. And I'll go ahead and distribute our n plus 1 squared over these 2 terms. And I'll do the same thing over here, being careful to subtract. So this is minus n to the 4th and minus n squared. I'm going to expand n plus 1 to the 4th using the coefficients from Pascal's triangle. That'll be 14641. So this is n to the fourth, 4n cubed, 6n squared, 4n plus 1. And then we'll expand this second squared binomial and subtract n to the fourth and n squared. We lose the n to the fourth terms. We're left with 4n cubed, 6n squared, 7, but then we subtract 1. So we're back to 6n squared. 4 plus 2, that gives us 6n, and our constant is 2. And let's go ahead and multiply by a half. So this is our expression for the left-hand side. Let's hope that this equals the expansion that we have on the right-hand side. Our right-hand side expansion was the sum of consecutive cubes. We'll expand this again using Pascal's coefficients. And we see that the expression is the same as what we had on the left-hand side. So I consider this proven, even though I didn't use induction. Let's take a look at their solution. If we reread the problem statement, we're supposed to guess the general law by these examples, express it in suitable mathematical notation, and then prove it. They didn't use the summation notation, which I guess it's okay. As a teaching tool, this book fails because it doesn't actually show the proof. Their observation that the left-hand side is an arithmetic progression, I'm wondering where they're going with this. Specifically, this is the sum of consecutive integers. Let's go on to the second problem. This is actually a pretty good hint. Oftentimes, when we want to write an arithmetic progression, we start with our first term is a, and our second term is a plus some common difference, and our third term is a plus 2d. But algebraically, you can save yourself a lot of effort if you make a be the middle term. A minus d is the term that came before, and a plus d is the term that comes after. Because if you're going to find the sum of consecutive terms in an arithmetic progression, then these d's are going to cancel out. This is a nice contest problem hack and allows you to solve for a, which here is 42. We can do something similar with our geometric progression. Instead of writing our three terms as b times the common ratio r, and br squared, we can make b our middle term. The term that came before that is b over r, and the term that follows is b times r. The sum of the two middle terms is 76. That's a plus b, and we can do our substitution for a and solve for b, which is 34. And now we need to find d and r. We are given the sum of the first terms of both sequences and the last terms of both sequences. So let's write that algebraically. This first one adds up to 85, and the second one adds up to 84. Let's substitute our values of a and b. Here, our method of writing our arithmetic progression comes in handy again, because when we add these two equations, the d variable is going to disappear. On the right, we have 84 plus 85. We can subtract 84 from both sides. Let's multiply the terms here by r to get rid of this fraction. And since it'll end up as a quadratic, we'll put all the terms on one side. If you're lucky, you'll notice that these three coefficients are all multiples of 17. So we'll divide by 17, which makes it a lot easier to factor. We want a product of 2, so let's put a 2 here and a 1 here. That'll give us 2r times 2, which is 4r, and then another r, so we'll make these both negative to give us minus 5r. Our two solutions for r are 1/2 and 2. Let's call these r1 and r2. Find our equation that allows us to solve for d. This second one looks like a good candidate. Solving for d in terms of r, we get this equation. We're going to get two different values of d depending on which value of r we try. So let's substitute r1, and we'll call this d1. 34 times 1/2 is 17, so d1 is 25. If instead we substitute our value for r2, we'll call this d2, and we get negative 26. Let's write out our two arithmetic and geometric progressions. For our arithmetic progression, our middle term again is a, so we'll put 42 in the middle, and we'll use d1 here, so we'll subtract 25 from 42 and get 17. Adding 25, we get 67. For our geometric progression, b is our middle term, so we'll put 34 here. Here we're going to divide by 1/2 to get the first term. That's the same as multiplying by 2. And then we'll take 1/2 of 34 to get 17. Let's see if this gives us the three sums that we want. Comparing to the problem statement, we find a valid solution. Let's see what happens if we take r2 and d2. Again, our middle terms are 42 and 34. This time we're going to subtract negative 26, which is the same thing as adding 26, so that gives us 68. And then we'll subtract 26 to get 16 for our third term. Our common ratio here is 2, so we'll divide by 2 and multiply by 2. We'll add these up again, and we get the same three numbers. So we've actually found two solutions to this problem. We're feeling pretty good about this, so let's take a little break. So let's see how much we can win. I found some historical tuition for Stanford. Since we're looking at 1948, that seems to be closer to this interval. So tuition then was $660, but I'm assuming that's also in 1948 $48. So let's see if we can translate that to the present. I found a website that will calculate the net present value. I have no idea if this is accurate for the inflation rate. If so, Stanford was a bargain back then, and tuition has exceeded the rate of inflation. Let's continue on with the exam. Looks like we have a geometry problem with some angles, so there's probably going to be trig involved. The way I interpret this problem statement is we have the peak of the mountain here at the top of this right triangle, and then we'll call these points on the ground A and B. And it says the lines of vision directed at these points include the angle gamma. So I'm putting gamma over here is angle APB. And then the inclination to horizontal is alpha and beta, so I'm assuming they go here. We're given that the distance between A and B is C, and we are asked for the elevation of the peak, which they're calling X. Again, here's the hint, and I don't find it particularly helpful, but I've seen problems like this before. I'm going to call this point Q, straight below the peak of the mountain down to whatever, sea level. I'm going to call the distance from Q to A, let's call it Y. We're asked to express X in terms of these angles, alpha, beta, and gamma. So we want to get rid of this Y. I can express alpha and beta in terms of some distances. For example, the tangent of alpha, that's opposite over adjacent, or X over Y. Similarly, the tangent of beta, opposite is X, adjacent is Y plus C. Since we don't want Y in our equation, I'm going to solve both of these for Y and then set them equal to each other. Since they're both equal to y, I'll now set these two expressions equal to each other and solve for x. I'll divide both sides by this factor and also multiply by -1. And we'll clean up these fractions in the denominator. And I get my expression for x in terms of alpha and beta and c. I didn't even use that angle gamma. Let's take a look at their solution. So here they use sine and the law of cosines, and they give us an expression for x squared. So let me check the problem statement. We're supposed to express the elevation x, not x squared. And anyway, this fraction seems a lot more complicated than mine. The problem statement did say to express it in terms of alpha, beta, and gamma. I don't have gamma in my expression, but if I really needed to include it, I could note that alpha, since it's an exterior angle to triangle APB, it's equal to beta plus gamma. And I can make that substitution for one of my tangent of alpha expressions, and now I have my expression that includes gamma in it. So I don't know. I don't find this solution very helpful. Let's go on to the fourth and final problem. This one looks pretty challenging. Weirdly, the problem writers include some extraneous information, which is not helpful at all. If we look at the hint, it points out that we need to find these three ratios, but we can find them in pairs. I find this to be trivial compared with the complexity of the rest of the problem. So let's sketch our tetrahedron. If we think about a sphere that's inscribed in this tetrahedron with sides consisting of equilateral triangles, this sphere is going to be tangent to the tetrahedron at the centers of these equilateral triangles. And the center of our sphere is going to be the center of our tetrahedron. So let's let P be the center of our sphere, which is also going to be the center of the tetrahedron. Let's let G be the center of this bottom equilateral triangle. In a regular tetrahedron, this vertex A up here is going to be collinear with P and G down here, just from the symmetry of the regular tetrahedron. So this distance from P to G is going to be the radius of our inscribed circle. If we think about the sphere that circumscribes this tetrahedron, it's going to be tangent at all the vertices, and it's going to share a center with the sphere that's inside the tetrahedron. So R2 is going to be the distance from P to A. Because we're finding ratios, for convenience, I'm going to say that the side length of our regular tetrahedron is 1. I'm going to draw BG. It's also going to be a median of this equilateral triangle that's the base of this tetrahedron. We'll call this midpoint C. If I draw this equilateral triangle separately over here, this is B to C, and then G is the center. It's going to be 2/3 of the distance from the vertex to the opposite side of this median, which is also the height of the equilateral triangle. The side lengths here are all 1, so this is 1, and CD is 1/2. The distance from B to C is 1/2 times √3. BG is 2/3 of this quantity. Now let's return to our tetrahedron, and we note that AG is perpendicular to BG because A is directly above G. Let's draw triangle AGB and fill in this distance. AB is a side, so that has length 1. We can use this to find the height of our tetrahedron, AG. So the height is √6/3. We want to figure out where P is, because P divides AG into the radius of our smaller circle and the radius of our bigger circle. Since the radius of our bigger sphere intersects all the points of our tetrahedron, then the distance from P to A is the same as the distance from P to B. That's also R2. Let's just call PG X. And since PB is R2, we'll call this root 6 over 3 minus x. And now we can use the Pythagorean theorem again, and we'll substitute. Let's combine like terms and solve for x. So x is root 6 over 12. And this is the radius of our smaller sphere. Let's find R2, the radius of the larger sphere, by using this equation. So we get R2 is root 6 over 4. Finding the ratio of R1 to R2, we get 1 to 3. Now we have a third sphere, so let's compare it to our second sphere that circumscribes our tetrahedron. Let's assume that the radius of this second sphere is 3. We'll put this sphere inside of the cube. When we do that, our sphere is going to be tangent to the sides of our cube in the centers of these square faces. And again, the radius here is 3, which means the side length of this cube is twice that, or 6, because it's going to be tangent to the opposite faces of this cube. Now let's draw our third sphere that surrounds this blue cube. This largest sphere is going to intersect the cube at its 8 vertices. I've drawn in pink here a radius of our smaller orange sphere. That has a distance of 3. Let's call this corner Q. The distance from P to Q is the radius of our largest sphere. We're calling R3. And triangle QAP is a right triangle. AQ is the distance from the center of the square that forms the top face of our cube to a corner of the square. Since the cube has side lengths of 6, this distance is 3, and the distance from A to Q is 3 root 2. So now we can find R3 with the Pythagorean theorem. So R3 is 3 root 3 when R2 is equal to 3. And that's true when R1 is 1. So our ratios are 1 to 3 to 3 root 3. Let's take a look at the provided solution. They seem to more or less have solved this similar to the way I solved it. They set the lengths of the sides of the tetrahedron equal to A instead of 1. I prefer 1 because it makes it a little bit easier without so many variables. But otherwise, I thought this was a pretty well-written solution. If you'd like me to solve any other contest problems, please leave them in the comments.